Hey, what's up, y'all? It's well, you already know who it is. Man, I really gotta get a, really gotta get an intro. So, in today's video, you're actually joining me somewhere different. We're on my iPad, and I'm just gonna draw a couple things before we actually get into the coding. It's gonna be a part two of our series, and I think today we're just gonna be making the agent shader. So, something nice, quick, and simple. Yeah. So, let's get into it. So the first thing we're going to want to do is, let's actually draw this out. So we were going to want a box of our screen. And our screen, we're going to have a positions array. And we're just going to be drawing positions, right? And these will be our agent. The real question is, what does each agent do? Well, if we draw one of our agents, it's going to look like this, because it's going to be a single pixel. And we're going to have three sensors, one in the front, one by some arbitrary length, we'll call theta, and same by another arbitrary angle, sorry, not length, and this will be the negative theta. So we're going to have three sensors, and they are basically going to sample what's in front of them. And based on the sensor, it will turn to the strongest, right? So if the middle one is greater than the left and the right, it turns to middle. So this is pretty simple. It's pretty simple behavior. We should see in a trail map of a diffused particle, our particle here with the sensors. This one will be the strongest, so it should actually turn in that direction. So how do we do this? Well, we should probably lay out our steps. So this first step, we're going to sense, and this is describing this behavior here with the sensing of sensors. Our second step is probably turn, and I think that's honestly it. That is it for our mold shader agent like behavior. So yeah, let's get into it. So last video we made a basic screen shader, and if I remember correctly, yeah, it just makes the screen black. So obviously, first things first, we want to open up, we actually want to activate our Python vim. So, just cd scripts, activate .bat, and then cd .dot, and then let's run it, main.py. Give it a minute, and yeah. Alright, so this is what we made last video, and we're just going to be improving upon it. So, first things we want to do is we want to optimize this as much as possible, at least a little bit. So let's first create a NumPy array. So let's say positions equals np.array. Yeah, we need NumPy, import NumPy as np. Okay, so let's make a positions array, and it's going to be a 2D array, and it's going to hold 4 values per: the x, the y, the z, which we will be using as heading, and w, which is just padding, because we have to have something, since it's going to be 3 vectors. If vec3 is true, does vec4 in GLSL, so we need that 0 for padding for the 16-byte alignment. So we're just going to do 100, 100. This will initialize at 100, 100 with a heading of 0 and 0, right? And now we want to create this as a MP float 32, since this will line up with 32-bit floats, which are the size of floats in GLSL. If they were 8-size floats in GLSL, we would, obviously change that around. So, first things first, we're going to want to come over here to RGB in our compute shader. You want to change this to RGB A8. Right, so now we have our thing, and everything should be working. Just double check. Yeah. The only reason we changed this is when we start working with more than one texture, you're going to notice it's just not going to work because that was a sizing alignment. The textures we work with are actual RGB A8, not RGB 32 float, because they have I think it's not the same size basically. And in Pygame shaders, he initializes them as RGB A8, and he uses that type of float 1, F1, because he never changes the alignment or anything. So more or less, we got to change that, and it'll still work the same, but it'll actually work. So the second thing we want to do is we want to make a buffer. So we're going to say layout binding 0 buffer, let's call it points, vec4 positions. I like to have the same name throughout, but you know, obviously you don't have to. And now we have these positions array. The reason we create a buffer is if we did an actual array, we would run into sizing issues very fast, especially since we are going to be using like a million agents. So the next thing we want to do is in our compute shader, we want to create a buffer. So buffer equals compute shader dot context dot buffer positions dot as type mp dot float 32 dot 2 bytes, and this creates our buffer. And then buffer dot bind to storage buffer, and we're going to want to bind to storage buffer 1 since it's a binding 1, right? So just make sure you change that in compute so it's actually binding 1. And yeah, now so when we dispatch this, it should have our binds and everything. So what we want to do here is we're just going to come down to compute shader dispatch, and we're actually just going to change this to length of positions. We're going to change these around later, but for now it'll just be this. And we're going to index our positions variable in our compute shader, gl underscore global invocation id.x equals vec4 of 1 0 0 1. So this will create if we change these all to 1, this will create a white dot on the screen at our position of 100 100. Syntax unreserved word void. Oh yeah, when you create our buffer, we need the semicolon. That's it. Undefined variable pixel chords. Right, so undefined variable pixel chords in pixel. We just want to say, so we actually did this kind of wrong here. Our coordinate is a vec2 pixel chords equals the indexed positions, so it'll be positions of that. There we go. And then pixel vec4 pixel equals a white pixel, so a vec4 of 1 1 1 1. And okay, so this needs to be ivec2, and then we just need to cast this. So ivec2 of this. Alright, there we go. Boom. 100 100, we have a white pixel. That's pretty nice, you know, we're looking good. And next thing to do is, why don't we just move it? So let's create a new variable, uniform float step. And we are just going to, you know, set that variable to something. But first, before we do any of that, let's make the pixel coordinates, and let's just multiply it by the vector 2 of, right, okay. So what we're going to do additionally is we're going to create an int heading. And we're going to create another vector 2, and this is just going to multiply into pixel coordinates. So I-vec2 will just be the cosine of the radians of heading, and we're going to be working with degrees when we refer to our heading, so we always have to convert and make sure. And then, you know, like everything else, times step and times step, and this should give us a nice step function. So we'll give it a heading. Yeah, we could just do it. We could just do it down here. So this is just for right now. So let's make the compute underscore shader dot. Yeah, compute shader underscore shader. Yeah, so let's do it right down here. Compute underscore shader index step equals, let's say 10, or we'll do 0.5, and then compute underscore shader of heading equals 0. This is actually about to change in a minute. We're just doing it to make sure. Compute shader is not, object does not support, oh, okay. Float step. Right. Let's dot program and dot program. Alright. And he's gone. So what happened here? The pixel coordinates are added instead of multiplied. And yeah, now he's just sitting there, which not what we were looking for, but it's definitely just because we're casting this. So it's going to be a vec2, and the thing is we're adding them all in pixel coordinates. So if we take this and we cast I-vec2 and we put it down in here, we won't need this pixel coordinates variable anymore. And then we could do just straight out of this positions and then plus equals that. So now it'll actually accrue. Yeah, see. So now it's actually accruing inside the pixel coordinates. Sorry, it's accruing inside our positions vector, which is bound to our buffer, and we're adding our heading times our step. So the next thing to do is get rid of our heading, and we actually want to create a, let's just create a variable for it. So heading equals the positions of GL underscore global invocation ID dot XYZ. Our heading is going to be our Z, and then we could just remove the uniform, and then out here just remove the heading so it doesn't throw an error, and it'll do nothing. You cannot call a non-function. That's a new one. Positions, oh yeah, so we actually want to index it, not call it. Okay. Excuse me. Yeah, so it does the exact same thing here. Now, the next step after this would be probably we want to make sure that we're not indexing outside of it. We could run into a lot of errors. So let's create a uint ID, which equals the, yeah, and then if ID is greater than or equal to our positions.length, then all we do is we just return. Right, so now this will keep us out, and then let's replace our ID with everything that has this. So ID, ID, and ID. And this just safeguards us in the future, but it does the exact same thing still. So boom, alright, we have agents. What we probably want to do now is we want to make the blurring. So let's create a new file and call it blur.glsl. And we'll just rip our compute shader code and then just gut our main and remove our point since we won't need it. And so since, just a quick thing, since we're not really doing anything with our screen, what we want to do is we want to come up here is we want to change this to 16, 1 and 1. So this matches our dispatch of 1, 1, and then our positions. And now it'll do the same thing still, except we're not using a work group. Like, our work group isn't going to be tall, air quotes tall, since we're not even using it. So it'll be more conducive to indexing this array and running in parallel. Now all we want to do is we want to create another shader. So we're going to call this a blur shader, and this will be a Pygame shaders dot compute shader of blur.glsl. We're going to create a blur underscore texture, which is a Pygame shaders dot texture of our blank surface with the blur shader context. Alright, and just for organization's sake, we're going to put our compute shader program with our agents and our actual compute shader, and we'll just try and keep these all together. And let's actually create our positions all the way up here. First thing we do. Alright, so now we have our blur shader and our, refactoring this so it makes a little more sense when we look back at it. We have our blur shader and we have our blur texture. So the first thing we're going to want to do is, the blur texture is actually the thing we end up drawing. So number one, change this blur texture. There we go. Blur texture as surface. Does nothing. That's it's actually what we wanted. So what we're actually going to do is we're going to just change our IDs around a bit. So we're going to source it, and then we're going to lay out RGBA8 binding equals 1 of our uniform image to the destination. Right. So now we're going to take from our destination and put it into our source, and we're going to dispatch now. So we want to come down here to we're actually going to probably want two textures for our buffer shader, or our blur shader. So let's create blur texture and then source underscore texture, which equals Pygame shaders, and then it's basically the same thing, but it's a source texture this time. And now what we want to do is our source texture dot bind 0, our blur texture dot bind 1, and then dispatch with our window size. So 600, 601. Now what we can do here is we want to kind of make these the same since they're the same height. Ideally, you could go in and you could change this to your aspect ratio, but we're just going to make these 8 and 8 since it's 600 by 600. So now we have our two textures bound to our blur shader, and all you want to do is we want to source from our blur texture, our source texture, and then output to our blur texture, draw our blur texture, which shouldn't be too hard. It'll be a little annoying, but it shouldn't be too hard. So what we're going to want to do is we're going to come up to our blur shader, and all we're going to do is we are going to take our vec4 pixel, an image load from our source of an IVEC2 of our GL underscore global invocation ID XY. Alright, so that's pretty much done with that. We get our pixel color, and all we want to do is image store to our destination, our IVEC2 GL underscore global invocation ID XY, and pixel color. That's it. And yeah, if we run this, don't forget your semicolons. No compatible structure. Too much data in the constructor. Right. It needs to be comma pixel. There we go. So we just we made a little oopsie. We include this in the IVEC2 on accident. So, all right, now we have again a black screen, but instead it's pulling from our source texture now and inputting into our main texture. So now all we have to do is write to our source texture and we'll get the exact same thing again. So if we come up to our main.py, all we have to do here is source texture.write. It's update. And we're going to update it with the contents of agents texture.addSurface. Okay. Should work now. Yeah, we get our little whatever it's called down here, our little guy who's just drawing his, his line. And you might have noticed, well, now it's flipped. So the way to, flip it again is we would just do pygame.transform.flip, and this will take our surface, it'll flip the X, true, flip the Y, false. So now we'll be flipping it sort of this way, right? And sorry, it flipped it over the X-axis. What we want to do is over the Y-axis. So false, true, actually. And there we go. Perfect. And it just it flips it every time it's drawn. For some reason, I don't really know why, but in any regard, all we have to do now is blur it and make a lot of them. So that's probably it for this video. We drew an agent to the screen. He's got a nice trail going. Everything's looking great. Next video, we are going to implement the blur. So we're going to blur the trail. We're going to make the agent actually turn and detect the trail chemicals and the path that the other agents have taken. And I think that should be it. We can do a little optimization revisit probably later on where we just, maybe we initialize the positions in a shader function or in its own compute shader instead of by a CPU, so that when we handle like a million agents, they're not, we're not looping over that a million times. But yeah, this is the basic compound, not compound, this is the basic function and functionality for our agents. You would just have to create a lot of them, blur the shader, and actually make them turn, and that'd be it. But that's all for this video, and don't forget to like and subscribe, and I'll see you next time. Bye.